Classical computers struggle to simulate more than 50 qubits. This means that a quantum computer with more qubits than that could potentially bring us quantum advantage. How about a machine with twice as many qubits? 100 qubits are here, thanks to ColdQuanta. Find out more about their amazing computer and how soon you can get a crack at running applications on it in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the president of quantum computing at ColdQuanta, and this company made some splashes in the news recently, so I wanted to have him come on. So welcome, Paul Lipman.
Great to be here.
Great, thanks. I don't know if you wanted to give us a quick background on your company.
Yeah, sure. So ColdQuanta is a quantum technology company. We've been in business since 2007. And the company was actually founded out of work done at CU Boulder, where our founder was part of the team that created the world's first Bose-Einstein condensate. And so we've been developing and manufacturing quantum technology since then. That applies both to quantum supply chain, quantum research, and now we have a quantum computing business. And that, I think, is the latest news that you were referring to in your opening comments.
Yeah, definitely. So it seemed like two companies appeared, not out of nowhere, obviously. You've been around for a long time, but all of a sudden it was like two companies claiming 100 qubits. So it would be Atom and you guys. So I don't know if you wanted to talk about how your approach to 100 is a little different than theirs.
So we're planning to release our first quantum computer named Hilbert, after the famous David Hilbert, at the end of this year. And that will be a 100 qubit cold atom-based, gate-based quantum computer. We'll make that available initially through our own cloud platform, and then later on in 2022 through some of the public cloud platforms as well, and seeing a lot of excitement and engagement from potential customers and partners around that platform. And I think one of the interesting kind of aspects of cold atom as a modality is in some ways it's the new kid on the block, right? There's been a lot of activity in the superconducting space and the trapped ion space, and cold atom is the latest one to take to the stage. But I think for a whole variety of reasons that we can get into, it is the most promising modality to truly over time achieve large-scale error-corrected fault tolerance. And so that's why you're seeing so much interest and activity in the area. As to the specific differences between our approach and atom computing's approach, we're using different atoms, I think is kind of at the core of the difference, but ultimately you'll have to wait for those devices to actually come online and actually run circuits and prove themselves in the market to really kind of dig into the specific differences.
Yeah, they're working, I believe, with the optical tweezer approach, which is starting to appear in certain types of systems. I love the name of your machine, Hilbert. that just comes up all the time in physics and everything, and exactly. You use Hilbert space, of course, to describe that giant space where other dimensional things can happen. So it's a pretty great, awe-inspiring name. But hopefully your machine is actually really here in this world and not lost somewhere in Hilbert space. It'll do a lot better.
Yeah, funnily enough, the actual lab where we're currently finalizing the build of Hilbert is named Hilbert Space. So
that's great. Yeah,
many a joke about infinite amount of space in that lab.
Yeah, so I don't want to get too lost in the physics jokes, but so your approach, if I understand it, involves using lasers to sort of slow down the atoms to make them cold, basically, to get below 5 Kelvin.
Yeah, that's right. It's actually to get below 5 microkelvin, so 5 millionths.
Of a degree, that's what I meant. Yeah,
so yeah. We're kind of 6 orders of magnitude colder than the kind of liquid helium-based approaches. So one of the real kind of core areas of expertise in ColdQuanta is this manufacture of ultra-high vacuum cells. We're one of the leaders in the world at doing that. And we provide that to other quantum companies, to research labs around the globe. And so at the core of Hilbert is one of these cells. You could literally fit it in the palm of your hand. And then we use various techniques for putting cesium atoms in that cell, and then a grid of lasers that trap the atoms in a 2D array. So you'll have a 10 by 10 array, 100 qubits. You could have a 20 by 20 array, 400 qubits, so on and so forth. And it's the lasers that are trapping the atoms in place and reducing their momentum, and thus reducing their temperature.
Yeah, it's sort of like a reverse microwave, right? You're using instead of your exciting particles to make them hotter, you're just slowing them down and chilling them quickly. So I assume that means a lot less machinery involved. This machine might not end up being in this giant cold environment. The IBM machines, they're giant cylinders that the chandelier is inside of, et cetera. Are you imagining this as being something that could fit in a rack or something one day?
Yeah, that's exactly right. So I think one of the, again, terrific advantages of the cold atom method is, and we can talk about the advantages around scalability and connectivity. One of the advantages is the fact that we don't need dilution refrigerators. So I think kind of interestingly, if you look at Google shared in their recent quantum symposium this graphic of a 1 million qubit device, and it was essentially the size of a basketball court, and all of which has to be frozen kind of to 3 Kelvin, 4 Kelvin, using techniques that don't even exist today. Whereas for the cold atom approach in our array, we could scale to hundreds of thousands, potentially even millions of qubits in something that would fit in the size of your fingernail. So, a single glass cell that would fit in your hand, and inside you could scale that up to hundreds of thousands or millions of qubits. And so ultimately, yes, the goal longer term is to reduce the form factor down to the size when it would fit into a couple of 19-inch rack-mountable units. And so if you think about that, that opens up really just a terrific array of potential use cases. So think of a quantum computer at the edge of a network, widely distributed, or quantum computers on satellites as part of a quantum communication network, or on airplanes, or on vehicles. So the ability to actually shrink these things down and deliver very high scale quantum computers, very high qubit counts, but do that effectively in a highly portable and low form factor would be, I think, open the industry's eyes and use cases which are probably not even in the consideration set today.
So you mentioned Google, and they were also talking recently about that ratio of physical to logical. And their latest guess, and it has to be a guess because Sycamore isn't that big, but they're guessing about 1,000 physical to get one good quality logical. Do you guys have any way of even guessing at how many physical you would need to get an error-free or a very low error logical qubit?
Yeah, one of the other advantages here of cold atom, so the way that we do entanglement with neutral atoms is through highly excited Rydberg states. So without getting into kind of the detailed physics behind it, what it essentially enables us to do is to have a high degree of entanglement at quite large separations within the array. So in our array, the atoms are separated by on the order of 3 microns. And the Rydberg interactions can happen over much broader distances. So we'll eventually be able to get to 50 to 1, 60 to 1, potentially even greater connectivity than that. And then if you think about error correction is a function of the configuration and the architecture of the qubit configuration, and also a function of this degree of connectivity. So we believe that the ratio of logical to physical qubits in our cold atom system could conceivably be an order of magnitude lower than that being posited for superconducting. So, to get to that 1,000 logical qubits to start to do really useful work, may conceivably only need 100,000 qubits. And again, we can do that in an extremely small form factor with extremely high stability.
Yeah, that's incredibly exciting. Do you have an approximate timeline for, let's say, that 100,000 down ratio time?
Yeah, so from a time frame perspective, I'll say, and maybe kind of pun slightly intended, we are laser focused right now on the launch of. Sorry, I had to get that in there. On the launch of Hilbert, which will be towards the end of this year. And I think if you start to look out from a time frame perspective, in the kind of 5 to 10 year time frame, really is when the whole industry is talking about reaching that 1,000 logical qubit milestone and the quantum advantage milestone, and we'll be right in that same time frame.
Okay, so you think you're kind of on track with, let's say, what Google was projecting. It's just you're going to need way fewer.
Yeah, and I think it's a combination of what has to happen to get there. So if you think about scaling up from 100 qubits to 1,000 to 100,000, you think about scaling up connectivity. There's certainly engineering work that has to happen to get there. We don't need breakthrough scientific discoveries on that path. So we have a high degree of confidence in our ability to continue to scale, to drive that growth in qubit count, to drive that growth in connectivity, to start to do some really interesting things with the form factor over the next several years.
Okay. So you're going to have this first machine, Hilbert, and you're going to have it available initially with some kind of private cloud, right? Before it's available with one of the bigger environments?
Yeah, that's right. And that's just really from a timing perspective. We'll certainly, as I say, that cloud will be a ColdQuanta cloud. It will enable customers to connect, to run circuits. We'll be supporting Qiskit and Cirq from day one. So customers will be able to submit circuits, run those circuits on the quantum computer, and we're in conversation with most of the major public cloud providers about integrating into their platforms as well.
That's pretty exciting because up till now, using Cirq hasn't really gotten you hardware access on the back end. It's been very much, look how pretty in my simulator. That's about it. No, that's pretty great. So they're languages that people will already know.
Exactly.
And do you envision what access would be like? Will it be some kind of like per shot system? Like, like if you have to run it, let's say for 1,000 shots or something like that.
Yeah, we're talking to customers right now about preferred business models. And what we're hearing for customers that want to do real work is kind of access for either on a dedicated basis for some period of time or block-based scheduling seems to be the preferred method. But we built the system in such a way that we can be agnostic to the overall business model and billing structure.
Okay, so you might be able to set up like an hour, really, if someone needed it.
Exactly.
Which could make some interesting queue times if people are like, "Where's the machine? It's gone." But yeah, availability is always a challenge. So you can imagine, because of the sizing, that one day people could have one in their own environment and then do something dedicated. Because I think real time is a big issue. Like when we're talking to customers about use cases, all these real-time ones keep coming up, and we just don't see a path for it right now. Like for example, fraud detection. We're working on better analysis of what might be credit card fraud, but if you don't have 24/7 access to a machine, you're not going to be able to actually implement something like this. So do you see a time where you're able to mass produce and get these machines in the hands of like large customers?
So I think to that point, the question of moving from today's model in quantum computing, which tends to be, and this is true, I think, irrespective of the industry vertical, very much a project-based kind of model, to one where these systems are really used in production, I think is one of the really kind of pivotal transition points that's going to happen here. And I think really as soon as the next year, we're going to start to see this happen, initially in some limited ways. And then I think once these have been demonstrated, really scaling that up. And so as you think about that, then the real model that I think will come to dominate in the short term is one where quantum is a piece of a classical production workflow, and where elements of a problem are being handed off to the QPU as part of this broader production system. But ultimately, that QPU needs to be available, as you say, on a 24/7 basis. So whether that is dedicated capacity that's running in the data center of the quantum hardware provider that is dedicated to that particular production process, whether that is a machine that is built and running on site within the data center of a more traditional hardware provider, or ultimately over time where these machines are mass produced and you see them running at the network edge. I think certainly in the short term, we're going to have some very interesting approaches that will emerge as these machines find their way into true production systems. And we're engaged in some of those conversations right now today. I think if you roll the clock forward and say, how does this play out kind of over the remainder of the decade, maybe in the 5 to 10 year horizon, then absolutely I think you'll start to see quantum computers take their place in the data center within the network, because the amount of the processing cycle that will get handed to the QPU will be an increasing part of the solution set. You know, the analogy, I've kind of become quite fond of this analogy in the AI space. I think what we saw happen really over the last decade in the development of AI was that there was kind of a confluence of factors, right? There was the development of the hardware, so the emergence of GPUs and ultimately of TPUs that were capable of handling this kind of complex linear algebra calculations that are at the heart of AI. There was the emergence of algorithms, tremendous development of AI algorithms, and also just an explosion of data for training. And it was those three factors that led to the growth and development and ultimately the business impact of AI and machine learning. I think in the quantum computing area, there's kind of a similar trifecta. There's one, the development of the hardware, right? And so ColdQuanta is absolutely part of that. New modalities, higher qubit counts, higher connectivity, and the whole industry is pushing in every part of the parameter space on the development of the hardware. The second is absolutely the development of algorithms, right? Some tremendous work happening on the quantum algorithms. And then the third important one, I think, is the development of use cases. And I think that's the area where we're just starting to scratch the surface of what the use cases are, not just on these kind of standalone problems, but ultimately truly in production. Where can NISQ-era devices actually add value as part of a real business production workflow in the near term? And I think that's where you're going to start to see the innovation happen over the next kind of year to couple of years, in concert with the innovation in hardware and the innovation of algorithms that will start to deliver some real business value.
Yeah, for now, it still feels very much like quantum computers are this like daily run. Like you can have a use case where it's, your end of the day settlement, or, this one optimization of a portfolio. You're just like, you're setting it up, you're doing it, and then you walk away because you don't have access all the time anyway. So yeah, I agree. The use cases will help determine where that goes. So have you been able to measure how the performance compares in any way? I mean, we could talk about quantum volume, we could talk about algorithmic qubits, like things like that, or maybe even benchmarking. Did you guys use any kind of real world analysis like that?
Yeah, I think the benchmarking question's a really interesting one, right? I mean, and I think we've thought a lot about what is the right benchmark. There's quantum volume. There's Atos is doing some interesting work with Q-score and others. And I think ultimately what you will see happen is it'll be a suite of benchmarks, because different benchmarks are measuring different things. To a certain extent, some of it's self-interested, right? Choose the benchmark that puts your particular device in the best light, even if it may not actually represent anything that has real meaning from kind of an end user perspective. And so ultimately, I think what we'll see, and we're part of a number of these consortia that are working on benchmarks to figure out the right set of benchmarks for actually comparing these devices in an apples to apples way. And we'll certainly be running benchmarks and issuing results on benchmarks once Hilbert is up and operational.
Okay. So there haven't been any initial guesses as to how it compares with like volume or anything like that. Um,
If anything, they would be guesses at this
yeah,
point, and so we'd rather share real data than
yeah.
supposition.
I like, yeah, for me, it's benchmarking all the way. I was, I would like to see going forward, like how many qubits and some kind of benchmark or
Yeah,
something like
yeah.
that. Because that,
But importantly, it has to be the right benchmarks, and it has to be multiple benchmarks, because you can always choose. You can create a benchmark, or you can choose a benchmark. But the question is, does that really mean anything, right? And the same thing is true in classical computing. It's not just one benchmark that the industry's gravitated around, but it's a whole set that ultimately kind of give you a full sense of the value and the utility of that particular device.
yeah. So let's talk a little bit about the software interface. So you said we could do, let's say, Qiskit. Um, do you have any kind of like simulator that you're going to like create so people could test their circuit and then apply it directly to the machine?
Yeah, absolutely. We'll be releasing a simulator actually in advance of Hilbert's release, and initially making that simulator available to customers. And that simulator will have the set of qubits, it will have the connectivity parameters, it will have the gate set, the noise characteristics to enable customers to run their circuits locally prior to running them on the hardware.
You'll be able to run this simulator just like you'll be able to download it and play around with it. It won't
Exactly.
be like
yeah, exactly.
just run locally.
Exactly.
So will you be able to simulate all 100 qubits, or because it's usually that seems to be a problem, right? Like going above a certain amount on like a laptop, maybe 20 or whatever.
It'll be obviously limited by the processing power of the device that you're running on. Simulating 100 qubits would be challenging computationally.
Yeah, I don't even think it's possible.
No, I mean,
yeah.
you let me know if you have a laptop that's that powerful. I'd like to get one as well. But yeah, and I think also one of the interesting kind of aspects of what we're doing with the cold atom approach is that we can do certain kind of gates that are just not available in other modalities. So, for example, global gates, right? If you think of an algorithm like QAOA that starts with a Hadamard across all of the gates, rather than having to apply those Hadamards qubit by qubit, with ColdQuanta, you'll be able to apply a single global Hadamard gate across all of the qubits in the circuit simultaneously. So those are the kind of things as well that we're building into the simulator to enable customers to really test out, okay, how would my circuit, how would my problem actually be applied with Hilbert once it's up and available?
Okay, so will this mean that you'll have some kind of customized tutorials for the way that you would, because right now if you go to Qiskit, you're going to have like the experience set up for the machines you might be running them on and the simulators you might be running on. Will there be some different ones that you'll like introduce to the community?
That's right. Yes, we're actually in the process of developing the programming guide right now.
Okay, yeah, because it sounds like it's going to be just a little different. And just like so, because it's Qiskit, for example, IBM does a whole bunch of reorganizing and then sometimes like rewriting your code before it gets down to that like pulse level. Is there then a layer in the stack? Do you guys have something similar? Is it completely rewritten, completely new? I'd imagine it'd have to be, right, to optimize this to actually control these qubits.
That's right. That's right. I mean, because the way that we the pulse level controls, obviously we're using lasers, we're using Rydberg excitation. That this is not microwave pulses issued to transmon qubits. So yes, under the hood, it's operating in a very different way.
Okay, so then thinking about that, like with IBM, I know you can go in and kind of manipulate that if you're more of an advanced developer. Will there be levels of like that kind of extreme customization, like going down and tweaking, or is that like in the future?
That'll be something that we will deliver as part of the roadmap. It won't be a day one capability, but certainly something that we're looking at for the near term.
Okay, yeah, because they did a lot of work recently on getting, I guess, all their software to just run faster. That I guess they claimed 100x speed up recently in the runtime.
What's interesting, though, I think if you look and you talk to customers, what we're hearing is actually what we're looking for is greater abstraction, not greater kind of individual pulse level control. And I think there certainly is a market for that. Some of the more forward-leaning and advanced organizations that have teams of quantum experts in-house who want to get down to that level of control. Certainly in the research community, a tremendous amount of interest. But I think as you think about how this scales up more generally, and you're talking to companies that are looking for applications of quantum in their business, in actual fact, they're kind of moving in the other direction.
Yeah, because we're seeing tools now that are starting to appear. StrangeWorks, Classic QAD, some others that are like, I guess, hoping to speed things up and make it easier for developers to just kind of like write and forget.
Right, exactly.
Are you talking to any of those guys about like tweaking the backend targets on their tools or anything like that?
Yeah, we're talking to all of the major software providers and platform providers. We'll be making some announcements there in the near future.
Oh, that's great. Yeah. I think that's important. I think if everyone gets too lost in the weeds, this industry will just like kind of stagnate.
Absolutely. I mean, look, I think at the end of the day, it will take some while before quantum computing is just another tool in the tool belt for the average programmer, for the simple reason that even for kind of folks who are fairly well versed in quantum computing, being able to explain what is a quantum computer good for, how is it different from a classical computer, what are the algorithms that can run, where are the best applications, is still a challenging question to answer, right? So there is a real place for those intermediaries to provide that abstraction layer that enables algorithm developers and programmers to incorporate quantum into the workflow in the right way, in the right place, and them to be, to a certain extent, agnostic about the underlying complexity. I think there's still tremendous work to be done there and value to be created. We have a team in-house of algorithm experts that work with customers to implement circuits, to develop circuits, but there's absolutely just a tremendous amount of value, I think, that comes from the interface with these software providers, because there's such a tremendous demand for that capability that vastly outstrips supply at the current time.
So by the time this airs, the simulator might be, imminently available or launching soon. When the actual hardware launches, will you be going public with? You don't have to say the name now, but would you be going public with like some company that's already tried some use case secretly? Like you hear like D-Wave, like, oh, Volkswagen cans of paint, like something. Is there some like kind of like out of the gate thing? I mean, of course, it's not a requirement for hardware. I was just curious if there was something like that would be appearing.
That's certainly the plan. I mean, we have a lot of interest in using Hilbert in testing circuits on Hilbert. And as I say, I mean, our principal focus right now is standing the service up, making it available, but at the same time engaging with customers to start to look at potential applications.
So as soon as we hit stop on the recording, you're going to tell me the customer. No, I'm kidding. But I'm sure there's a couple already.
Maybe I'll come back in another episode and talk to you with the customer about the actual results.
Yeah, that's of course of interest. And so you've been doing some internal playing around. Do you feel like there's any one use case right now just that you can abstractly talk about that shows promise, that maybe even in this very iteration of Hilbert might show some kind of advantage soon?
Well, so I'll separate the question of approaches that show promise from the question of advantage, because I think the question of advantage is a much deeper and more nuanced question. In terms of the approaches that are showing promise, I think the two that we're most excited about in the near term, and this is not massively dissimilar from others in the quantum computing arena, is in terms of optimization problems, and by virtue of the fact of the large qubit count, and also some very interesting problems in quantum chemistry that we're looking at right now. Okay.
And are you going to have anything like, let's say like D-Wave has their hybrid approach, which is where it actually has classical computing built in that parses some of the jobs over to the machine. Are you going to have something dedicated and built like that, or will it all be up to the customer to develop that side of it? like whatever has to be done classically as part of like a workflow?
So our principal focus, I would say maniacal focus at this point, is building world-class quantum computers and driving as hard as we possibly can to scale and to scale in the dimensions that I've talked about. And so in terms of the classical components of the workflow, we'll be doing that either in partnership with customers that have pre-existing classical systems and classical infrastructure, or with partnerships with providers who will take the classical part of the infrastructure and look to ColdQuanta to provide the quantum part of the solution. So we won't be building our own classical environment, but rather partnering with others to do that. And that's for the simple and important reason that there is so much work to do in building and developing and scaling quantum computers that we need to remain focused on that really tremendously enormous task of building and scaling in this really exciting field.
Laser focused, yeah.
Laser focused. And I got you, hey, listen, many other puns I could give you. It's really cool stuff we're doing. I could go on for the rest of the podcast with those jokes.
Yeah, and it sounds like just because of the slight different approaches we talked about, you might already have some optimization to the optimization problems in the form of how, your Qiskit setup will be, the types of gates you can do, things that are unique to your machine.
That's right.
Yeah, I just feel like with the software stack, there's always so much more you can get out of a new piece of hardware. So I always like to hear kind of what folks are doing in that respect. So this sounds like an amazing machine, and I can't wait to get my hands on it. So I want to try and get access as soon as possible. I know that. For Tivity, I know we'd love to try some experimentation on this thing. Definitely.
Yeah, absolutely. I would love to get you on it, and I'll extend an invitation if you're ever out in Boulder, Colorado, or want to make the trip out there. We'd love to have you, show you the lab and show you the computer in operation in the flesh, so to speak. It's really a tremendously impressive feat of science and engineering to actually see. It's one thing to like command line or web interface and submitting jobs. It's quite another to actually see the machine in operation.
I'm going to take you up on that because it is a physics nerd's dream come true to be able to say he moved through Hilbert space. So.
Absolutely. Absolutely. Came out the other end. That's
intact. So with that little silliness, I'll let you go. Thanks again, Paul, for coming on, and talk to you soon.
Very nice talking to you. Thanks.
Thanks to Paul Lipman for joining today to discuss ColdQuanta. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's constant with a K, hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also find information on our quantum services at www.protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.